Hello everyone, welcome to the Exam 3 review for Introduction to Statistics 1. Now, this exam usually has a little bit more material on it, but we have a very short period of time between our second exam and our third exam this semester because of Thanksgiving break. Because we're going to have our exam following week, we have our makeup exams, and then we couldn't push it back a week because then we would be falling into the break time. So we're going to jump right in. This is going to mostly focus on Chapter 5, which actually isn't a problem because the stuff that we're learning now about normal distributions is going to be super important for pretty much almost everything else we're going to be doing. So looking at this practice exam, the first set of questions is going to be some review questions, some concepts, things like that. The first question says, given the mean of a normal distribution, how can you find the median? So in order to find the median for a normal distribution, right, it doesn't say that it's skewed or anything like that. So we're going to assume that it is a perfectly symmetric and bell-shaped distribution where it is centered at the mean. Well, if you have this perfectly bell-shaped and symmetric distribution where it is split perfectly in the middle by the mean, the peak here will also be the mode. So the mean equals the mode, but it also is going to be half the data is going to be to the left, half the data is going to be to the right. So this means that wherever the mean is, this should also be roughly equivalent to the median. The second question asks, describe the inflection points on a graph of a normal distribution. At what x values are the inflection points located? So again, in this case, we have a normal distribution. And if we think about the nature of our bell-shaped graph for a normal distribution, we're centered at the point mu. And then the inflection point is when it goes from being concave down to concave up, which is where it sort of changes the direction of the slope. So anyone who's taken calculus, you would know that concavity is based on the second derivative, right? The first derivative tells us the direction. The second derivative tells us whether that is getting more negative or whether it is getting more positive, whether it's in the positive or the negative direction. So in this part, we have that it's concave down. And then to the sides, we have that these are concave up. So the inflection point is where it goes from being concave down to concave up. So that would be right here and here. And the way that we find this is that this concave up is going to be at mu plus sigma. And concave down is going to, or rather the other left side is going to be mu minus sigma. So you can find your inflection points of your normal distribution based on wherever it's centered, and then going out by one standard deviation to each side. That'll be the inflection point where it starts going from concave down to where it starts increasing, so that's concave up. The third one says, draw two different curves that have the same mean but different standard deviations. So in this case, it means that if we have a normal distribution centered at some mean mu, then if we have a different distribution centered at the same mean mu, it means that the peak will be in the same location. So what you can do for this one to draw another distribution that has the same mean mu, but a different standard deviation is either you could have a larger standard deviation, which means that you'll have a lower peak at mu, and you'll have fatter tails. Or what you could draw is you could draw a distribution that has a smaller standard deviation, which means that it has thinner tails, but it has a higher peak. So it'll come down quickly, and then it will peter off to the sides. So these are two different ways you could draw something like this. And it didn't specify saying that the standard deviation went up or down. So in this case, this would be actually three different distributions that all have the same mean, right? Because if I were to split this at the mean mu, they should all peak at the same spot. But the standard deviation determines how wide, how much it distributes to the left and to the right. So of course, because the area under each of these graphs all has to be equal to 1, this means that as you get a larger standard deviation, it means your peak has to decrease. If you get a smaller standard deviation, your peak would have to increase to keep the area under the graph equal to 1. Problem 4 asks, why is it correct to say a normal distribution and the standard normal distribution? And this is because if you think about the fact that our normal distribution, n, is determined by two parameters, mu and sigma. That is where it's located, that's the center of it, and how spread out it is, its deviation, or in this case, standard deviation. So based on the fact that we have continuous data, it means that there's technically an infinite number of normal distributions based on these two parameters, right? Because if I have continuous data, so anywhere on the number line, I could have any number of points that is the center of my graph. And because there's an infinite number of possibilities, there's also an infinite number of distributions based around each of those points. So there's an infinite number of normal distributions. So that's why when we talk about the normal distributions, we say a normal distribution because it's one of many distributions. The standard normal distribution is different though, because there's only one standard normal distribution. And that is when you have a normal distribution which specifically is centered at 0 and has a standard deviation of 1. So this standard normal distribution, 0, 1, there's only one of it, hence the standard normal distribution, while there's a normal probability distribution. Question 5 says, a z-score is 0. Which of the following statements must be true? A, the mean is 0. B, the corresponding x value is 0. Or C, the corresponding x value is equal to the mean. So this one is actually going to be C. And this is because if we have a z-score of 0, right? So think about your z-score. Your z-score is on the standard normal distribution, which is the distribution that is centered at 0. So if your z-score is equal to 0, when you would transform this back to whatever normal distribution you were from, your data came from, right? Any z-value that's to the left would be on the left of the normal, left of the mean on the normal distribution. Any z-value that is to the right would be on the right side of the mean on your normal distribution. So if you have a z-value of 0, this would mean that it falls exactly at the mean. If we were to look at our z transformation, we have z equals x minus mu over sigma, because it's specifically asking about some outcome x. So for z to be 0, that would mean that x would have to be mu, so it'd be mu minus mu over sigma, which would be 0 over sigma, which is just equal to 0. So this means that it would have to be C, where x, our value that we have, would have to be equal to the mean mu. Problem 6 says, a group of 192 students voluntarily signed up for a research project. The standard deviation obtained from the results of the research is 17. What is the standard error of means? So standard error of means is just going to be the standard deviation divided by the square root of n. So in this case, we had a total of 192 students, so that's our n. And our standard deviation that we ended up with was 17. So plugging this into our calculator, we get 17 divided by the square root of 192, and we get a value of 12.2686. So I'm going to say 269. Problem 7 asks, what are the requirements that must be met in order to approximate a binomial probability distribution with a normal distribution? So in order to approximate a binomial probability distribution with a normal probability distribution, you have to have sufficient size to assume that it follows a normal distribution. So what we use in this class, you will see other places where it's a little bit different. We use NP is greater than or equal to 5 and NQ is greater than or equal to 5. Now, in some other resources, you may actually find that they use the value 10. But the idea of this is that if your p-value is very centered on your histogram, right, on your binomial data, that then you won't need as large of a sample size, right? Because, for example, if my p was 0.5, then I could just multiply this by 10, and I get 5, which is greater than or equal to 5. If I multiply 10 times q, well, q is 1 minus p, so this would also be 0.5. This would also give me 5, which is greater than or equal to 5, and both of these check out. If, for example, though, instead I had something like a p-value of 0.9, right? So if I did the same thing, 10 times 0.9, I would get 9 for my NP, which does, in fact, end up with a value that's greater than or equal to 5. But if I did my NQ, this would be 10 times 0.1, which would be equal to 1, which is not greater than or equal to 5. So this one would fail. So in order to compensate for that, what we'd have to do is we would need a bigger sample size. So the idea of NP and NQ being greater than or equal to 5 or 10 is that we're saying that based on the skew of the data, the further p deviates from 0.5, right? Because 0.5 would be a perfectly symmetric histogram. As p shifts, if p is close to 0.0 or close to 0, it would be very right skewed because most of the data would be on the left. If we have that P is close to 1, we would have the data is very left skewed because most of the data is on the right. So the tail goes off to the left. So in this case, we would need NP greater than or equal to 5 and NQ greater than or equal to 5. Now, one thing I want to point out here is that it's very important that you have this word and, not or. Or would mean that if one of these is true, we're good to go. And that's what we'll do whenever we're using our assumption checks for different things, right? We'll look at things like, do we know that this comes from a normal distribution, or do we have a sufficiently large sample size? But for this, both of these must be true. If one of them fails, you cannot use normal approximation to a binomial probability. If both of them are true, then you can. Number 8 asks us to state the central limit theorem. So I'm going to kind of shorthand it here, but there's two main parts to the central limit theorem. So we have our central limit theorem, and we have that if our population is known to come from a normal distribution. So if this is true, then we have a couple different things from this. One, we know that our distribution of sample means, so we have our X bar distribution, this is capital X, by the way, capital X bar. So our X bar distribution is normally distributed. So I'm just going to put that it's normal. 2, we know that our X bar distribution has a mean of mu. And 3, we have that our X bar distribution has a standard deviation of, which is the standard error of means, is going to be sigma over square root of n. So this is the first part of our central limit theorem. If we know that our data is coming from a normal population, then regardless of the sample size, so no matter what our sample size is, our sample size could be 1, this is still going to be true. The second part is, if it's not known to come from a normal distribution, then, so population not known to be normal. The reason I say known to be normal is because we're not saying that it's not normal. We're just saying that it might not be normal, or it might just be that we don't know. So if we don't know, we need to make sure that we have a sufficiently large amount of data, because this says that if we have a sufficiently large amount of data, then our X bar distribution will approach the normal distribution. So why is this important? Well, because a lot of times this is what we're going to check to see if we can actually use a normal distribution when we're doing certain things. For example, when we get into confidence intervals and hypothesis testing, this will be what helps us determine whether we have enough data or if we know it comes from a normal distribution, therefore we know we can use a normal distribution. Specifically, we're going to be focusing on this part of if it's known normal. The way we kind of shorthand this is sigma known? If we know sigma, we know that it came from a normal distribution. Or in this case, if we have sufficiently large data, well, if we're assuming that it's bell-shaped and symmetric looking, then this would be n is greater than or equal to 30. But as I talked about in our classes, I don't want you to think of this number as a rule that it has to be n greater than or equal to 30. This is something that is a convention that we use in class, because if we have symmetric and bell-shaped data, there's actually a reason why we use this number, and it is pretty accurate. But remember that this holds true in the real world regardless of your distribution, right? It's just not known to be normal. It could be some other distribution. But the more it's skewed away from a bell-shaped symmetric graph, the more your sample size would need to be. So while basically every statistics text uses n greater than or equal to 30, I don't want you to get locked in on the fact that this is some hard rule. This is based on these kind of toy problems. We're assuming that if we were to graph this, it looks bell-shaped and symmetric, but we're not really sure that it's a normal distribution. But the central limit theorem holds regardless. It's just saying that you have to have a larger and larger n, and if it gets sufficiently large, then we will assume that it does in fact follow a normal distribution. Problem 9 says, 2 binomial experiments are given below. For each experiment, determine whether you can use a normal distribution to approximate the binomial distribution. If you can, find the mean and standard deviation. If you cannot, explain why. So for part A, we have 22% of adults over 18 years of age have a bachelor's degree. You randomly select 20 adults over 18 years of age and ask whether they have a bachelor's degree. So this one's pretty straightforward. We just go up to 20 people, we say they're over 18, and we say, do you have a bachelor's degree, yes or no? And we know that the probability that they do is going to be 0.22. So based on this P of equal 0.22 or 22%, we can find Q by taking 1 minus P. So 1 minus 0.22 is going to give me 0.78. The way we check whether we can use a normal distribution to approximate a binomial probability distribution is we're going to use NP and NQ. And we're going to see if they are greater than or equal to 5. So for NP, we said that we were asking 20 adults. So I'll just write that here, n equals 20. So this is going to be 20 times 0.22. So 10 times 0.22 is 2.2, and we got twice that. So this is going to be 4.4, and then this one is going to be 20 times 0.78, which is going to give me 15.6. So the NQ is large enough to say, yes, it looks like we're going to use our normal distribution. But our NP is not greater than or equal to 5. This one fails. Both of them must be true in order to use a normal approximation. So this means we cannot use Z. So we cannot use Z. Our second example says, in a survey of U.S. college students, 74% believe that colleges do not have the right to restrict the expression of political views on campus. You randomly select 20 college students and ask them if they believe colleges have the right to restrict expression of political views. So in this case, now what we have is we have an N of 20 still. We're asking 20 college students, and we have a probability of success that they would agree with this statement of 0.74, which means that we have a probability that they would not agree with this of 1 minus P, which in this case would be 0.26. So again, we're going to do NP, and we're going to find NQ. So NP, again, is going to be 20 times 0.74. 10 times 0.74 is going to be 7.4. So 7.4 times 2 is going to be 14.8. And NQ is going to be 20 times 0.26. So 2.6 times 2 is going to be 5.2. So both of these together, right, 14.8 is greater than or equal to 5. That's good. 5.2 is greater than or equal to 5. That's good. This means that we can use Z. So this question says, if it does allow us to use the normal distribution to approximate our binomial, we need to then find our mean and our standard deviation. So to find the mean, what we're going to use is we're going to use the fact that mu equals n times p. Well, we've already actually found that because when we're checking our assumptions, we already checked NP, and we know that this is going to be equal to 14.8. And then our standard deviation, sigma, is going to be the square root of n times p times q. So we just plug those values in. We have 20 times 0.74 times 0.26. And then I'm going to plug that into my calculator, and let's see what we get. So 20 times 0.74 times 0.26, and I get a standard deviation of 1.9616. For part B, we're going to do some true or false questions. We're going to determine whether each statement is true or false, and if it's false, we're going to rewrite the statement to make it true. So number 10 says, as the sample size increases, the mean of the distribution of sample means increases. So this is going to be false, because remember that the mean of a distribution of sample means has a mean, right? We said our X bar distribution has a mean of mu. So as my sample size increases, this has no effect on my distribution, the mean of my distribution of sample means. It does affect my standard error of sample means, but it does not affect the mean. So in this case, it would be as the sample size increases, the mean of the distribution of samples remains the same. It doesn't change. Number 11, as the sample size increases, the standard deviation of the distribution of sample means increases. In this case, this is false. This is because if we look at our standard deviation of sample means, this is going to be sigma over square root of n. So this means that as my square root of n increases, what happens to the entire fraction? Well, if I have a fraction where the denominator is getting bigger, that means the entire fraction is getting smaller. So in this case, it would actually be that as the sample size increases, the standard deviation of the distribution of sample means will decrease. Number 12 says a sample distribution is normally distributed only when the population is normal. Now, based on our central limit theorem, that's not true. That is false, right? Because if our population data is normally distributed, then yes, our sampling distribution would also be normally distributed. But we also had that if we had sufficiently large sample size, meaning that this would be false because if we have sufficiently large sample, it will also be normally distributed. This is our n greater than or equal to 30 part of the central limit theorem. Number 13 says, in a geometric distribution, random variable x counts the number of successes. This is also false. For a binomial probability distribution, x counts the number of successes. For a geometric distribution, x counts the turn at which you have your first success, meaning that your x can be 1, 2, 3, ... up to any number of turn, right? So there's this countably infinite possibilities. Though the further you go down, eventually you get really infinitesimally small probabilities. Unlike a binomial, which can have 0 successes, you can't have the 0th turn for a binomial or geometric distribution, meaning that this one, if you wanted to correct it, would be it counts the number of turns for your first success. So the next part of our exam, which is the bulk of it, we're going to be looking at doing some computations. So 14 says, suppose that the average time it takes for students to complete an exam is 63 minutes. So that's going to be our mean. That's the average time it takes students to complete an exam. And it has a standard deviation of 7 minutes. So we have sigma equals 7. A random sample of 36 students was taken. Assume the scores are normally distributed. So this means that we have n equals 36. Question A asks, what is the probability the mean time is less than 60 minutes? So first thing we're going to do, we're going to set up our problem, right? This is the what are you solving for step. So it's the probability of, what is our symbol here? Well, we're looking at the average score. So we're doing a distribution of sample means, which means that we're taking the probability of x bar. It says, what is the probability that the mean time, that's another way you can look at it, if it says mean or average, the mean time is less than 60. So we want less than 60. Okay, so now we've translated from the problem statement into the mathematical definition of what it is that we're solving. The next thing we're going to do is we can't really solve this without using integration, but in this course we don't use integration, so what we're going to do now is we're going to do a transformation. So we have the probability of, now I need to do an z transformation. So the z transformation for a problem with x bar is going to be z equals x bar minus mu divided by sigma divided by the square root of n. So in this case, this is what I'm going to write. I'm going to take my x bar, I'm going to subtract mu from it, I'm going to divide by sigma, and then I'm going to divide that by the square root of n. My inequality does not change, and now I'm going to plug in my values. My x bar that I'm looking at, that boundary value, is 60, minus, we're going to look at our mean mu that came from the original part of the problem, 63, divided by 7, divided by the square root of 36. Now, before we even jump over to doing your calculation, you can look at this and know whether you're going to have a positive or a negative z-score. So I have 60 minus 63 in the numerator of my fraction. That is going to give me a negative z-value. So that kind of helps prep which z-table we need to be using. The positive z-values looking to the left or the negative z-values looking to the left. But also, it's a good way of knowing which side of the graph you're on. Okay, so now let's plug it in. So once we've done this transformation, x bar minus mu over sigma divided by square root of n, this is now just going to be equal to z. My inequality does not change. And now I need to figure out what this is. So 60 minus 63 divided by 7 divided by square root of 36, which is equal to 6. Now, one thing I'll caution you with on this is if you're putting this into a calculator all in one step, be sure to put parentheses so that it doesn't do 60 minus 63 divided by 7, something like that. So what I'm going to do is I'm going to do parentheses 60 minus 63, end parentheses, divided by, open parentheses, and then my 7 divided by 6. And this is going to give me a z-score of minus 2.57 14285, blah, blah, blah. But remember, for z-scores, you always want to have them in terms of 2 decimals because that's what's on our table. Now, looking at this, can we look at this up on one of the tables that we supply to you? Yes, because we gave you 2 different z tables for this exam. The first one is going to be when you have positive z values and you're looking at probabilities to the left. And we give you one that has negative z values looking to the left. So this means that because this is negative and it's looking to the left, this does fit into one of our tables. So we need to go to our table to find the probability to the left of negative 2.57. Okay, now looking at our table, on the left side, we've got our negative z values in units and tenths. Along the top, we have our hundredths place. So we're going to go down to negative 2.5. We're going to go over to 0.07, and we get 0.0051. Okay, so that was part A. Part B of this question says, what is the probability the mean test time is between 61 and 65.5? So we're going to set this up. We have 61 is less than or equal to, x bar is less than or equal to 65.5. Now, just like before, we need to do our transformations. So this is going to end up being the probability of 61 minus 63 divided by 7 divided by the square root of 36. Inequality stays the same. X bar minus mu over sigma divided by square root of n. Inequality stays the same. And now we do same thing for our larger value. 65.5 minus 63 divided by 7 divided by the square root of 36. Okay, so now we plug each of these into our calculator and we get our values. So again, for this one, I'm going to do parentheses 61 minus 63 divided by open parentheses 7 divided by 6, close parentheses, hit equals. And I get that my first value is going to be negative 1.714, so negative 1.71, less than or equal to x bar minus mu over sigma divided by square root of n. This is now going to be equal to z. And then I find my second value. So parentheses 65.5 minus 63, end parentheses, divided by open parentheses 7 divided by 6. And I get this is equal to 2.142, so 2.14. Now, to find this, we first have to now split this into 2 different inequalities. And this is because whenever we have something like this, right, we have our z values, right, this is on the standard normal now. We have a z value that's on the left over here somewhere, and we have a z value that's on the right over here somewhere. And if I want to know what is the area between these two to get my probability, I'm actually looking for everything to the right of this z that is also to the left of this z. So it'd be this interval right here. The problem is, though, is we don't really have an easy way to find that using the same inequality, what we have right here. So what we're actually going to do is we're going to use the fact that I can take all of the values to the left of my larger z, and I'm going to subtract off all the values to the left of my smaller z, and I will be left with that same interval. So we're just using a difference function. So in this case, this actually becomes the probability z is less than or equal to my larger number, 2.14, minus probability z is less than my smaller number, negative 1.71. So this is the one thing you got to be careful with here. Yes, in the original probability, z is greater than or equal to negative 1.71. But when we switch it to our difference function, this becomes less than or equal to, sorry. Remember, that doesn't really change anything for continuous because equals to is infinitesimally small, equals 0. Okay, so now can we find both of these? Yes, right? This is positive, looking to the left. That's one of our tables. This is negative, looking to the left. That's another one of our tables. So now this is going to be equal to, we go to our z table, and we're going to find the probability to the left of 2.14. So looking at our table here, we go down to 2.1, we go over to 0.04, and I get a probability of 0.9838. Minus. Then we go to our negative z table. We're looking for the probability to the left of negative 1.71. So we go down to negative 1.7, we go over to 2 to 0.01, and we get 0.0436. And then, of course, I'm just going to plug this into my calculator. I get 0.9838 minus 0.0436, and I get a probability of 0.9402. For our last question for this one, we have part C, which is, what is the probability the mean test time is greater than 62? So probability x bar greater than 62. So this becomes probability of x bar minus mu over sigma divided by square root of n. Inequality stays the same. Plug in my values, 62 minus 63 divided by 7 divided by square root of 36. So this is going to be equal to the probability of z is greater than, so we plug this in, open parentheses, 62 minus 63, which of course is going to be -1, divided by parentheses, 7 divided by 6, close parentheses, and I get -0.857, so -0.86. Okay, so can we look this up in our table? And the answer is no, because remember, we have a positive and a negative z table that we supply to you, but they're always looking to the left. So if we kind of think about, this is what we're actually trying to find. We are looking for the probability to the right of some negative z value. So in order to find the probability to the left, what we're going to do is we're going to use the complement. We're going to take everything, and then we're going to subtract off everything to the left of that z value, and we'll be left with whatever's to the right of that z value. So this is going to be equal to 1 minus the probability z is less than or equal to -0.86. So again, this we can look up in our table. It's negative and it's to the left. So this is going to be our negative z table. So we go there to figure out what is our probability that z is less than -0.86. So looking at our z table here, because I haven't zoomed in so everybody can actually hopefully see the numbers, you can't actually see the top. But if you had this table in front of you, you would be able to. But if you look at the columns, it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I went down to -0.8, and then I went over, so 0, 1, 2, 3, 4, 5, 6, and I got a probability of 0.1949. But I'm not done yet, right? Because if we look at it, I need to take that's the probability to the left of my z value, but I need to get the probability to the right. So I need to subtract this from 1. So I'm going to go, well, actually I don't need this, 1 minus 0.1949, which is going to be equal to 0.8051. And that's our probability to the right of, with the z value of -0.86. For problem 15, we have a survey reports that 47% of people in a certain city use public transportation to commute to work. If we randomly select 220 people from this city and ask each of them whether they use public transportation to commute to work, what is the probability more than 113 say yes? So first thing I'm going to do is I'm going to write down my given information. So given, we have 47% of people in this city commute to work. So that is the probability, if I were to randomly go and ask somebody to use public transportation, that they would say yes. And of course, because of this, right, I can also figure out my Q. Q is going to be 1 minus P, so this is going to be 0.53. It says that we're going to go randomly ask 220 people whether they commute to work. So our N is 220. And then I'm actually going to jump down a little bit for this part. We want to know what is the probability that more than 113 would say yes. So the probability that if I were to go ask these 220 people, that more than 113 would say yes. So this is going to be a binomial probability distribution problem, because if we think about it, there are two possibilities, right? They either say yes or they say no. They say yes with a probability of 0.47. They say no with a probability of 0.53. There is a set number of trials, the 220 people. You can think of each of them as a trial, right? So person 1, do you take public transportation? Yes or no? Person 2, person 3. These are independent trials because each of them will have this probability of success for each one, and it doesn't depend on what the other people said. So in this case, this is a binomial probability problem, but I don't want to solve this using binomial probability distribution, because I would have to figure out what is the probability of 114 saying yes, 115, 116, 117, all the way up to 220. And that's a lot of calculations to do. So what I want to do is I wanted to use the normal approximation to this binomial probability. So the first thing I need to do is I need to make sure that I can. So I'm going to check my assumptions, which my assumptions are NP and NQ being greater than or equal to 5. So I need to show that this is true. So if I have 220 people, and I multiply that by 0.47, and I have 220 people, and I multiply that by 0.53, this is going to be equal to 220 times 0.47 is 103.4, and then 220 times 0.53 is going to equal to 116.6. Now, I want to make two quick points here when you're checking these assumptions. There is actually one alternate to this assumption, which is in the problem, if you actually were given the raw numbers, how many people said yes, how many said no, in which case you would find your p by using p hat, because you're estimating it, using how many said yes over the total number. And this would give you your p value. And then from there, you could figure out your q hat value by subtracting it from 1. If you were to then do this, all you're doing is undoing the operation you just did and getting back to the raw number. So you also could use the fact that if you have the raw numbers, if x is greater than or equal to 5 and x complement is greater than or equal to 5, this would also work for checking your assumptions. The other thing is I wanted to kind of point out is that when you find NP, right, we got 103.6. Well, this has to make up, P and Q have to make up all of the possibilities. They either use public transport or they don't. So once I found this 103.4, then basically the NQ had to be whatever 220 was minus this 103.4. That would have to be how many said no. So if I were to go out and ask 220 people, then I would expect on average 103.4 would say no, and 116.6 would say yes. But going back to our actual assumptions, 103.4 is greater than or equal to 5, so that's good. And 116.6 is greater than or equal to 5, so that's good. So this means that we can use our standard normal or our z distribution. So now to do this though, let's actually go back to our probability. Probability x is greater than 113. Well, we have to consider though, is when we have discrete data, if I said probability x is greater than 113, that means that if I had some, histogram of all this, let's say that this is 113. Well, probability of discrete data greater than 113 would be everything that is greater than, not including 113, which would be everything to the right, but not this rectangle. But if I were considering a normal distribution, when I say 113 greater than, it's the same thing as saying everything to the right of this, which means that now we have a part that's not being counted. So the first thing we need to do is we first need to get this in terms of greater than or equal to, so that we're in the right area. So this is going to be the probability x is greater than or equal to 114. So before, when you have your discrete data, you have to get it first into terms of or equal to. But now we've run into another problem, because now what we're saying is, for the discrete data, is we're looking at everything here, like I originally marked in. But for our normal distribution, it's going to look at this point right here, which means that we are missing this part of our probability, which we want to include. So what we're going to do is we're going to do a correction for continuity. Now remember, for your correction to continuity, you are going to add or subtract 0.5 to your value for your probability. And the direction, whether you add or subtract, is based on whatever would cause you to increase the area of your probability, right? Because basically what's going to happen is you're splitting a rectangle in half. So if I'm looking less than, I'm missing the upper half, which means I would need to add 0.5. If I'm doing greater than, I'm missing the lower half of my rectangle, which means I need to subtract 0.5. If I'm looking at the probability between two values, I would need to subtract 0.5 from one side, add 0.5 to the other side. Or if I wanted the probability of exactly one value, I would both subtract and add 0.5 for correction for continuity. So in this case, because I'm doing greater than, I need to subtract 0.5 to include that part of the rectangle. So this is going to be equal to the probability of x greater than or equal to 113.5. Now, the reason I want to caution you, though, not to see that there's some pattern here where it's like, oh, I just added 0.5. No, because this won't be true if I gave it to you already in terms of greater than or equal to. So just to make sure you don't make any mistakes, always first convert it to greater than or equal to, or less than or equal to in this case. And then what you do there is then you do your correction for continuity. So if you have a probability that's greater than, you subtract 0.5. Less than, add 0.5. If it's between two values, add and subtract 0.5. And if it's one value, add and subtract 0.5. Okay, so now we actually have our probability we're solving. Let's do our z transformation. So this is going to be equal to the probability of x minus mu over sigma. Inequality stays the same. My x value is 113.5. But you'll notice when we had our problem set up, we were not given a mean mu or a standard deviation sigma. So what we're going to have to do is we're actually going to have to solve those. So we're going to use the fact that the expected value of a binomial distribution, which is the mean, is going to be equal to NP, which we actually already solved. We have that it's 103.4. And then our standard deviation is going to be the square root of n times p times q, which is going to be the square root of 220 times 0.47 times 0.53. So plugging this into my calculator, I get square root of 220 times 0.47 times 0.53, a value of 7.4028. So now I'm going to plug these values in. I have 103.4 divided by 7.4028. And this is going to be equal to the probability of x minus mu divided by sigma is just z. My inequality does not change. And then I'm going to figure out what this is going to be. So this is going to be parentheses 113.5 minus 103.4 in parentheses divided by 7.4028. And I get a z value of 1.364, so 1.36. Okay, next step, we need to look this up in our z table. Can we look this up in our z table? Well, we have a positive value, so that tells us which table we're going to have to use, but it's looking to the right. We need to be looking to the left. So we're going to do a transformation. We're going to use the complement, and this is going to be equal to 1 minus the probability z is less than 1.36. This we can look up in our table, right? Because we have our positive z values. We're going to go to our positive table, and we're looking to the left. So let me pull up the table, and we'll figure out what that's equal to. Going to our z table, we go down to 1.3, we go over to 0.06, and we get a probability of 0.9131. So this is going to be 1 minus 0.9131, which then is going to give us a probability of 0.0869. Problem 16 says, the weight of apples in a grocery store is normally distributed with a mean of 151 grams and a standard deviation of 20 grams. If a random sample of 64 apples is selected, Part A, what is probability that their average weight is less than 144.6 grams? So this is going to be another probability where we're going to be looking at the average weight or mean weight, meaning we're doing the distribution of sample means. So first thing I'm going to do is I'm going to write down my given information. So I have that the mean of all the apples is 151 grams. And the standard deviation is, so let me just add that, grams. The standard deviation, sigma, equals 20 grams. We have a total of n equals 64 apples, and we want to know what is the probability that the mean weight is less than, so probability of x bar, mean weight, less than 144.6. So just like we did before, first thing we're going to do is our transformation, probability of x bar minus mu over sigma divided by square root of n. Inequality stays the same, and we plug our values in. 144.6 minus 151 divided by 20 divided by the square root of 64. So now doing this, I'm going to plug this into my calculator. Square root of 64 is just equal to 8. So this is going to be, open parentheses, 144.6 minus 151 divided by, open parentheses, 20 divided by 8. and I'm going to get a z value of probability z is less than, inequality is the same, negative 2.56. Can I look this up in one of my tables? Well, I have the negative z value, which means I'm going to use my negative z table, and it is looking to the left. So the answer is yes. So let's go to our table and let's figure out what this probability is equal to. So going to the side, we have negative 2.5. We go over to the column that's 0.06. We see where they intersect, and we get a probability of 0.0052. Part B asks, what is the probability that the average weight is at least 148 grams, so at least less than or equal to, and at most 159.3. So now what I'm going to do is I'm going to, just like before, do my transformation. So this is going to be equal to the probability of 148 minus 151 divided by 20 divided by the square root of 64 less than or equal to x bar minus mu over sigma divided by square root of n less than or equal to 159.3 minus 151 divided by 20 divided by the square root of 64. Let's figure out what these values are. So going into my calculator, I have open parentheses 148 minus 151 in parentheses divided by open parentheses 20 divided by 8, and I get negative 1.2. Inequality stays the same. X bar minus mu over sigma divided by square root of n is going to be equal to z. Inequality stays the same, and now I'm going to plug these values in. So I have open parentheses 159.3 minus 151 divided by open parentheses 20 divided by 8 close parentheses 3.32. Now, of course, I can't look this up directly in my table, so what I need to do is I need to use my difference formulation, which is going to be the probability of z less than or equal to the bigger number, 3.32, minus probability z is less than or equal to, remember the sign, the inequality changes here, negative 1.2, which of course, because our z values had to have 2 decimals, what we're going to be looking in the table is going to be negative 1.20. You don't have to add the 0 when you're doing the test, just I want to do this so everybody can follow along what we're looking for on the table. I can look this up in my positive z value table because looking to the left. I can look this one up in my negative z value table because looking to the left. So let's figure out what these are. So for my first value, I go down to 3.3. Now, of course, remember, again, this is zoomed in just so it takes up a good amount of the screen, but we can count the columns to figure out how many to go over because we want to go over to 0.02. So it's 0, 1, 2, meaning it's the third column. This is going to give us a probability of 0.9995. So 0.9995 minus. Now we need to go to our negative z table and figure out what is probabilities left of negative 1.2. So jumping to our negative table, we go down to negative 1.2. We go over to the first column, which is 0.00, and we get a value of 0.1151. So now we just need to figure out what is 0.9995 minus 0.1151, and we get a probability of 0.8844. Okay, for number 17, it says, from a medical study, it was found that the systolic blood pressure of adults in a certain region roughly follows a normal distribution with a mean of 120 mmHg and a standard deviation of 13 mmHg. So I'm going to write down this given information real quick. We have a mean mu of 120, and we have a standard deviation of 13. And the questions ask us to find x such that the probability of z greater than some value a equals 0.8389. So we're actually looking for the probability that x is greater than some value. We already used a, but in this case, I'm just going to leave it as a. And we want to know what is the probability that this is 0.8389. Now, don't confuse this with the a that's in the problem, because that a value is going to be whatever z value causes this to be true, and then we're going to convert to our x value. So this is what we're going to be looking for, is this x value, a. So it's why reason it's written a little bit differently than how I teach in class, because usually in class I focus on the a being the value, the cutoff value that we're looking for, which is in terms of x, In this case, it's saying you have some A value where the probability of Z is greater than this A is 0.8389. What would that correspond to as an X value, which is the same exact question. So what this is just an inverse normal probability problem. So the first thing we need to do is we're going to graph our normal distribution. Let's figure out where the Z is going to be. So if I'm on the standard normal, where would my Z value need to be so that 83.89% is above, right? And so this means that my Z value would have to be somewhere down here on the left. And this is because I have greater than, so it's sort of like I'm filling it from the right. And then remember that at 0, this accounts for 0.5 of the data. Well, 0.5 of the data is not big enough for 0.8389, which means that I would then need to continue going to the left until I got to some value of Z on the left, which has 0.8389 above it. Now, here's the thing though. Now that we know that this Z is on the left, we know that our Z is negative. But we can't look up what Z would cause this to be true on our table. Why is that? It's because our table only tells us what falls to the left of a Z value. So we actually are going to have to figure out if this area of this part of the curve is 0.8389, that means that we need to figure out what this part to the left of that Z value would be. So in this case, it would be 0.1611. So this is actually what we're going to be looking up in our Z table. Now, the fact is that we have a negative Z means we need to go to our negative Z table and we need to find the probability 0.1611. Now, unlike when we were doing our probabilities previously, where we had a Z value and then we figured out what the probability is, now we're going to find the probability and then go out to figure out what the Z value are. Going to our negative Z table, we find, you can see here I've highlighted it, 0.1611. We go over to the left side and we're going to get a negative 0.9. So our Z is negative 0.9. And then we would go up this column. Well, since this is the last column, even though you can't see it on the screen, this is going to be our 0.09. So we have a Z value of negative 0.99. Now, in order to actually figure out what the A value is, or X, based on the question, that corresponds with the Z value, right? Because the way the question was written, we had probability Z is greater than some A equals 0.8389. Well, guess what? You've just found that. That negative 0.99 is that value. But we want to now say, okay, but I want to transform this back to my normal distribution, which is centered at 120, which I know that because it's on the left of 0, that I'm going to have some value over here, and this is the value that I want to figure out what it is. So I need to basically do a transformation from my standard normal to my normal distribution with a mean of 120 and a standard deviation of 13. So the way we're going to do this is we're going to use, I'll write it as X just to keep it consistent with the problem. X is equal to mu plus Z sigma. Now in our case, using this, right, we have X plus mu sigma. So we have X equals, we plug in mu, 120, plus negative 0.99. So minus 0.99 times, and then sigma, which is 13. So we plug this into our calculator and we get 120 minus 0.99 times 13, and we get an X value of 107.13. For the next problem, we're doing the same thing, except for now we have the probability, I'm just gonna write it the way the problem has it. Z is less than A equals 0.9306. So again, I'm going to draw a normal distribution, standard normal, centered at 0. Where would the Z value need to be so that 93% of the data falls to the left? Well, it's going to have to be over here, right? Because this would be 0.5 of the data, which means that this would have to be the other 0.48 something or other. So this is where my Z is going to be. Z is positive. So can I look this up in my table? Yes, I have my positive Z table and I have a probability to the left. So I need to go to my Z table and find the probability 0.9306. Okay, looking at the table, I've highlighted 0.9306. So we go over to 1.4, we go up to 0.08. So this Z value is going to be 1.48 and it's positive. So plugging this into my X equals mu plus Z sigma to get it back in terms of my actual normal distribution, this is going to be x is equal to mu, which is 120, plus 1.48 times my sigma of 13. And this is going to be equal to, so we do 120 plus 1.48 times 13, and we get an x value of 139.24. Same thing, I need to find probability of z less than a equal to 0.3300. And then from that, I will then figure out what the x value is associated with that on our normal distribution. So we have our standard normal, centered at 0, and I need to know where would 0.33 or 33% of my data be to the left. Well, that means that my z value is going to be down here, right? Because if I were doing less than, it's like I'm filling it up from the left. If I were to get all the way to 0, I would have 0.5 of the data, or 50% of the data. That's too much, meaning that my z would have to be somewhere before I get to 0, meaning z is negative. Now, can I look this up in my table? I can, because it is looking to the left. So let's switch over to our z table and let's figure out where it is. As I've done before, I have highlighted 0.3300, and this gives us a z value of negative 0.4, and then we go over 0, 1, 2, 3, 4, gives us a z value of negative 0.44. So we're then going to figure out what is our associated x value. So x is equal to mu, which is 120, minus 0.44 times 13, which is going to give me, so 120 minus 0.44 times 13 is going to give me 114.28. And then all of these answers are in terms of our original problems, which, remember, in this case, this was MMHG, and this one is in MMHG. So in this case, our cutoff value would be 107.13 MMHG. And this would, for the second one, our cutoff value would be 139.24 MMHG. And for our last one, our cutoff value would be MMHG. And I keep calling it a cutoff value because you can think of this sort of as your boundary where this probability would be true. And once we have this value, we could actually take this, plug it back into probability of x less than 114.28. And if you were to solve for this, you should get a probability of 0.3300. Now, sometimes it's not always going to be exact because, remember, the shortcoming of our tool, the z table, is that it only goes to 2 decimals, but there's nothing to say your z value can't be more decimals, meaning that sometimes if you land between 2 probabilities, you're going to have to pick the closest z value, in which case you will have a little bit of rounding error. You'll still get very close to the actual probability you started with, but it might deviate a little bit if it wasn't exactly on the table when you found that first probability. Problem 18. In a survey of U.S. college students, 74% believe that colleges do not have the right to restrict the expression of political views on campus. They randomly select 20 college students and ask them if they believe that colleges have the right to restrict the expression of political views on campus. Find the probability that less than 11 students agree with this view. Okay, so for this one, this is again going to be a normal approximation to binomial problem. So we have our p of 0.74, which means that we have a probability of failure, that they disagree with this, of 0.26. We have a total of 20 college students that were asked, so n equals 20. And first thing we need to check is we need to check whether we can even use a normal approximation for this. So we're first going to do n times p, which is going to be 20 times 0.74, which is going to give me a total of 14.8. And then we have NQ, which is going to be 20 times 0.26, which is going to be 5.2, right? And the way I knew this is because I took that 0.74, so I knew that if it were 10 students, it would be 7.4. I multiplied that by 2, got 14.8. And then I knew that if this is 14.8 of the 20 students on average, that means that the rest would have to be NQ, which is where the 5.2 came from. 14.8 is greater than or equal to 5. 5.2 is greater than or equal to 5. This means that we can use z. Okay, so now let's set up our problem. The problem says find the probability that less than 11 agree with this view. So we want the probability that x is less than 11. But remember what we talked about previously is that when we have discrete data, the probability x is less than 11 is the same thing as saying the probability that x is less than or equal to 10. You have to do this though because the probability that x is less than 11 is not the same as probability x is less than or equal to 10 for continuous data. It would just be the probability x is less than or equal to 11, in which case you would have that gap where you would cause your probability to be incorrect. The other thing I want to mention though is if these assumptions were to fail, you would have to use the binomial probability to find this. So this is something you could calculate, right? You could calculate the probability of 0 said yes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you could find the actual probability. That would actually be more precise than this because when we have our histogram of discrete data and we overlay a normal distribution on top of it, you're going to have little bits that are over and under counted, right? Because if you think about the fact that these are made up of rectangles, when I have a normal distribution that goes over it, I'm going to have these areas that are overcounted and these areas that are undercounted. And of course, the bigger your sample size is, the smaller those gaps will be, the closer the approximate value will be. But there will be still, that's the reason we say normal approximation to a binomial probability, not the normal probability of a binomial probability. It's an approximate probability. Okay, so next thing we need to do though, is we need to do our correction for continuity. So because we are doing less than or equal to, this means that we need to increase by 0.5. So this is going to be probability x is less than or equal to 10.5. Okay, so now this is going to be probability of, we're going to do our transformation. So x minus mu over sigma is less than or equal to 10.5 minus, okay, now we need mu. So to find our mu, right, mu is equal to n times p. We already found that. It's 14.8. So 14.8 divided by, now we need to figure out what our sigma is. So our sigma is going to be the square root of n times p times q, which is going to be the square root of 20 times 0.74 times 0.26. So we're going to plug that into our calculator. So 20 times 0.74 times 0.26. And I got a standard deviation of 1.9616. So 1.9616. And of course, I'm doing this to 4 decimals just because we want final answers in 4 decimals. So we're just going to keep it, just help prevent some rounding error. So probability of x minus mu over sigma is just equal to z. Inequality stays the same. And now I'm going to plug this into my calculator. So I have 10.5 minus 14.8 divided by 1.9616. And I get a z value of negative 2.192, so 2.19. Can we look this up in our table? We sure can, because we have a negative z value and we're looking to the left. So let me switch over to our z table and we'll find that real quick. Okay, on our z table, if you look, I've highlighted the probability, right? We go to, on the side, we go to negative 2.1. We go over to 0.09, we see where they intersect, and we get a probability of 0.0143. Problem 19 says to find the indicated area under the standard normal curve and then show all transformations needed to arrive at your answer. And then from there, we'll find our probability. So for part A, it says to the left of z equals negative 2.14. So this means that we're looking for the probability that z is less than, because that would be to the left, of negative 2.14. Now remember, when you're using continuous data, the less than or equal to are equal to each other because probability of z equal to negative 2.14 is equal to 0. So regardless of which one you do to set it up, this won't be an issue. Now looking at this, we have probability of a negative z value and we're looking to the left. Now if you remember, we have 2 tables that we're supplying for the exam. We have the positive z values looking to the left and we have the negative z values looking to the left. So therefore, this means that we can actually look this one directly up in our table. So I'm just going to put table, meaning no transformations needed. And we're going to set all these up before we jump to the tables to actually find them. B says we want to find the probability to the right of z equals negative 0.46. So we have probability of z to the right means greater than negative 0.46. So now going back to our first problem, if we were to draw this as a standard normal, this would just be, we have our standard normal, so centered at 0, and we have a negative z value, and we're looking for a probability to the left. So this is one we can look up in a table. This one, we have, again, a standard normal, centered at 0, and we have a negative z value again, so our z is over here, but we're looking to the right, which this is not one of the tables that we supply for you. So there's two ways you could actually solve this. What you could do is you could use the complement, which is to say that you would take the entire distribution, right? So you take everything minus everything to the left of that z. So if this is 0, this is that z. If we subtract off everything to the left of that z from everything, we'll be left with just what's on the right side. Or what we could do is we could do the same idea, except for now we could solve it using symmetry, which is to say if we took the z value and we flipped it, the fact that it's a mirror image on the left and the right, we could change this to everything to the left of positive z, right? Because if I took this z here, when I flip it, this negative z becomes positive z. So we have a negative z here, we have a positive z here. So there's two ways we can actually find this. We could set this up as 1 minus the probability z is less than negative 0.46, which, because it's complement, it actually becomes less than or equal to, right? Because complement is everything that's not in the original statement. Well, we had everything greater than negative 0.46, so this would be everything less than or equal to 0.46. We can look this up in our table. Or we could set this equal to probability that z is less than positive 0.46. For the next problem, it says to the left of z equals 1.82. So this one is probability z to the left or to less than 1.82. So then in this case, we can actually use our table for this, right? Because we have a positive z value looking to the left. That's one of the tables we give you. So I'm just going to write table. So then drawing this, just to keep it consistent with everything else, this is just going to be, right, our standard normal. We have a positive z value, and we are looking at everything to the left of this, and that's one of our tables. The next problem is we want everything to the right, so that would be greater than 0.39. So drawing that, this would be a positive z value, meaning it's to the right of our 0 on our standard normal, and we're looking to the right. So this is not one that we could look up in our table. So again, you have two options. We can use complement, which would then be everything minus everything to the left of this z value, and we'll be left with what's to the right of it. Or you could still use symmetry just like before, where instead of having it to the right of the positive z value, you flip it and it becomes to the left of the negative z value. So this means that this could either be found by doing 1 minus the probability z is less than 0.39, or you could set it as probability of z less than negative 0.39. And then our last one, we have the probability of z between negative 1.34 and 2.16. So we'd say negative 1.34 is less than or equal to, z is less than or equal to 2.16. So looking at this, what we're doing is this, right? We want everything that is between our negative z value we have here and our positive z value we have here. So you could think of this as between two values a and b. So if I want everything between these two values, what I'm actually going to do is I'm going to take everything to the left of my bigger value, subtract off everything to the left of my smaller value, and then I will have the probability between the two. So in order to do that, this is going to become the probability of z is less than 2.16 minus the probability of z is less than the smaller value, negative 1.34. Now remember, I know it's that z is greater than that negative 1.34 in the original probability. But when you split this, doing the difference between them, you have to change the sign to less than. So looking at this, probability z is less than 2.16. I can look this up in my table, our positive z table to the left. Probability z less than negative 1.34, again, I can look up in my table, in this case, my negative z table. So now that we have this, let's actually go and figure out what all these probabilities are. So the first one, we have the probability z is less than negative 2.14. So we go to our negative z table, we go to the left side of our table, we look at negative 2.1, we go to the top, we find 0.04, we see they intersect, and you can see I have it highlighted here, it equals 0.0162. So for the next one, we have 1 minus probability z less than or equal to negative 0.46, or we could do probability of z less than positive 0.46. Now, I'm going to use the less than the negative version because I already have the negative z table up. So in this case, I'm going to solve for this. This is going to be 1 minus, and now I need the probability that z is less than negative 0.46. Looking at our table, we have negative 0.4 on the left side. Now, you can't actually see the top because I have zoomed in enough so you can see it. So this is the sixth column because remember, or rather it's the seventh column because remember it starts at 0. So you go 0, 1, 2, 3, 4, 5, 6, and we get a probability of 0.3228. So 0.3228. So 1 minus 0.3228 is going to give us 0.6772. For the probability that z is less than 1.82, we can look this up in our positive z table to the left. So we go down to 1.8, we go over to 0.02, and we get a probability of 0.9656. So 0.9656. For the next one, we have probability of z greater than 0.39. We can do probability 1 minus probability z is less than 0.39, or probability of z less than negative 0.39. So again, I'm going to go with the complement just because I already have the positive z table up on my screen. So this is going to be 1 minus, and now I got to figure out what the z value is. So looking at our table, we have 0.3, we go over to 0.09, and we get a probability of 0.6517. So 1 minus 0.6517 is going to be 0.3483. And then just to show you that this is equal to the same thing, what I'm going to actually do is I'm going to go and find the probability of z less than negative 0.39, just to show you that they do give the same answer. So looking at our negative z table, right, I have negative 0.3, go over to the last column, which is 0.09, and we get 0.3483, which matches what we got when we used the complement. So like I said, both of these are acceptable answers for a problem like this. So last one, we had probability of z less than 2.16 minus probability of z less than negative 1.34. So now we need to go to our positive z table to find this one and our negative z table to find this one. So I'm going to do the second one first since I already have the negative z table up. So looking at our negative z table, we have negative 1.3, go over to 0.04, and I get a value of 0.0901. So this is going to be minus 0.0901. And now let's go to our positive z table to find the probability z is less than 2.16. So the probability of z less than 2.16, we go over to 2.1, go over to the 0.06 column, we get a probability of 0.9846. So this is equal to 0.9846 minus 0.0901, and this is going to give me, so I'm going to plug this in, 0.9846 minus 0.0901, and I get a probability of 0.8945. Problem 20 says in a survey of 19-year-old women, their heights were normally distributed with a mean of 63.9 inches and a standard deviation of 3.3 inches. So first thing I'm going to do is I'm going to write this down. We have a mu of 63.9 inches and a standard deviation of sigma equals 3.3 inches. Part A says, what is the probability that a randomly selected participant has a height less than 57 inches? So we know we're looking for a probability, and we're looking for a height that is less than 57 inches. So now the question is this x or is this x bar? Well, usually if it's x bar, obviously the question should have average or mean, right? The mean height or the average height of a sample of women. In this case, though, it's talking about a specific participant, meaning of all the people I could select, if I randomly were to select one, so one means a single output or outcome. So this would be X. So we're looking for the probability that X is less than 57. And as a reminder, when we're looking for the probability of X, we're going to be using the Z transformation. Z equals X minus mu over sigma. So we're going to use that transformation. So this will be the probability of X minus mu over sigma, and our inequality is going to stay the same. And now we're going to plug our values in. So 57 minus 63.9 divided by our standard deviation of 3.3. So I'm going to plug this into my calculator, right? So I'm going to get probability of X minus mu over sigma. This can be Z less than, and I need to figure out what the value is. So looking at my calculator, I'm going to do parentheses 57 minus 63.9 in parentheses divided by 3.3. And when I plug this in, I'm going to get negative 2.0909. So because of that, because our Z values, because of our table, have to be 2 decimals, this is going to be minus 2.09. Now, can we look this up in our table? We can, right? Because this is a negative Z value looking to the left, and that's one of the tables we have. By the way, I'm going to set all these problems up, and we'll find the actual probabilities all at one time when we're on the Z tables. So part B says that what is the probability that a randomly selected survey participant has a height that is between 60 and 65 inches? So this is going to be probability of 60 less than X less than 65. So similar to what we did last time, we're going to do probability of 60 minus 63.9 divided by 3.3. And our inequality stays the same, less than. And now we're going to plug in X minus mu over sigma, that's our transformation for X, less than, and we plug in our 65 minus 63.9 divided by 3.3. Now looking at these really fast, 60 minus 63.9, we know that this is going to be a negative Z value. 65 minus 63 is going to give us a positive Z value. So that means we know that this is going to be a negative and this one should be a positive. So again, we are going to grab out our calculator, and this is going to be open parentheses, 60 minus 63.9 in parentheses divided by 3.3, and I get negative 1.1818, so that's negative 1.18 less than X minus mu over sigma is going to be equal to Z, less than, and now we plug in this value. So this one is going to be 65 minus 63.9 divided by 3.3, and I get 0.33 repeating, which rounds to 0.33. Now, at this point, what we can do is, because we have the probability between two values, we have to actually change this to the probability of Z is less than the bigger value, 0.33, minus the probability Z is less than our smaller value, negative 1.18. I can look this up in my positive Z table because it's to the left. I can look at this in my negative Z table because it's to the left. So both of these we can look up. Now, one thing I want to point out before we move on to part C is you could actually do this split right here. So if we were to do that, you would get the same thing, because this would become the probability of the bigger number, right? So X is less than 65 minus the probability X is less than, because remember your inequality does change when you do your difference, so less than 60. And then whenever I am finding this, right, this is going to become the probability of X minus mu over sigma is less than 65 minus 63.9 divided by 3.3 minus the probability of X minus mu over sigma is less than, and then we have 60 minus 63.9 over 3.3. 3.3. I don't know why I put an extra 3 there. And if we look at this, this is just going to be this term. This is just going to be this term, and we actually get the exact same thing. Part C says, what is the probability that a randomly selected participant has a height that is more than 70.5? So C is going to be, what is the probability that X is more than 70.5? Following the same steps we did before, this will be the probability of X minus mu over sigma. Inequality stays the same. 70.5 minus 63.9 divided by 3.3. So I'm going to plug this into my calculator. So I have open parentheses, 70.5 minus 63.9 divided by 3.3, and I get a value of probability z is greater than 2. Now, you can leave it as 2, but I'm going to put 2.00 so everyone can easily follow along, because we know that for our z table, we need 2 decimal places. So when we look this up, we're going to go down to 2.0, go over to 0.00. Can I look this up in my table? Well, the answer is no, because it's looking to the right. So we have 2 possibilities. We can use the complement like we did in the last problem, or we could use symmetry, which will allow us to just use the negative z table. So I'm going to do that one for this. So this would be the fact that I'm looking to the right of 2 would be exactly the same by symmetry as looking to the left of negative 2. So this will be probability z is less than negative 2.00. So now that we have all 3 parts of our probability set up, let's actually go to our z-tables and figure out what these are. So for our first probability, we had the probability of z less than negative 2.09. So we go to our negative z-table, we go down to negative 2.0, go over to 0.09, and we get a probability of 0.0183. Now, while we're here already on the negative z table, I'm actually going to figure out what this probability of z less than negative 2 is, because I'm already actually even on that line. Going right back to our z table, it's literally we go to negative 2.0, but we stop at the first value, which is 0.0228. And now let's focus on part B. So our first probability, we're going to be on our positive z values table. Our second probability, we're on the negative z values. So again, we already have the negative z table in front of us. So let's actually figure out what this one is first. What is the probability of z less than negative 1.18? So looking at our table, going down to negative 1.1, going over to 0.08, we get a value of 0.1190. And now for our last thing, before we can actually solve for what this probability is, we need to figure out what is our probability z is less than 0.33. So now that we're on our positive z table, we go down to 0.3, we go over to 0.03, and we get a probability of 0.6293. So now we have 0.6293 minus 0.1190. We're just going to plug that into our calculator, and we'll see what we get. So 0.6293 minus 0.1190, I get a probability of 0.5103. Problem 21 says to determine whether you can use a normal distribution to approximate the binomial distribution. If you can, use the normal distribution to approximate the indicated probabilities. If you cannot, explain why and use a binomial distribution to set it up, but do not solve the indicated probability. So it says, in a survey of US adults, 19% said that they have participated in a clinical trial. If you randomly select 20 US adults, find the probability that the number who have participated in a clinical trial is between 15 and 18. So in this case, we have the 19%. That is the probability that if I were to randomly select one of these individuals, that they have been in a clinical trial. So this is our probability of success. P equals 0.19, which because of this, we want to get our probability of failure. This would be our Q, which is 1 minus P. Our Q would be 0.81. Right? Because together, our probability of success and failure, because this is really the complement of this, would be equal to 1 if you add them together. So 0.81 plus 0.19 equals 1. Next thing we need is our number of participants. So this would be 20. So now we need to check whether we can use our normal distribution to approximate our binomial distribution. So in order to do this, we need both NP and NQ to be greater than or equal to 5. So let's see what those are equal to. So I'm going to plug in NP, this is going to be 20 times 0.19, and NQ, which is going to be 20 times 0.81. So 0.19, if I were to multiply this by 10, would give me 1.9. And then if I were to multiply that by 2, because I have 20, not 10, this would give me 3.8. Next one, we have 20 times 0.81. So again, 10 times 0.81 gives me 8.1, times 2 gives me 16.2. And you can double check this because both of these numbers together should add up to your total number of participants. So 16.2 plus 3.8. So 16 plus 3 is going to give me 19. 0.2 plus 0.8 is going to give me 1. So 19 plus 1 is 20. So we're good. Now, looking at our NQ, this one is greater than or equal to 5. So this works. But looking at our NP, this is not greater than or equal to 5. So this one fails. In order to use the normal approximation for a binomial, both NP and NQ must be equal to 5. Now, the reason this fails is because if you look at our probability of success, 0.19, this is a pretty low probability of success. It's closer to 0 than it is to 0.5, meaning that we would need a larger sample size in order for it to meet the threshold for both NP and NQ. So for example, if we had gotten 50 participants, in that case, we would have a big enough sample size in order to use normal approximation. But because we don't, this means that we can't assume that if we were to make a histogram of our binomial probability distribution, that it would be able to be replicated by a normal distribution overlaid on top of it. The next thing we need to do is we need to figure out what the probability is using the binomial distribution, because if this fails, that's what our alternative is. We have to use the binomial in its original state. So it says we want to find the probability that between 15 and 18 of the participants have participated in a clinical study. So this means 15 and 18. And we have our outcome X between. Now the question is it going to be less than or equal to? Well, because it says between and it doesn't indicate that it's included, this is going to be 15 is less than X is less than 18. And our binomial data is discrete data. So when we say X is greater than 15, that means that it's everything that is more than 15, but not including 15. So that would mean, remember, for discrete data, there's nothing between 15 and 16. So if I say everything more than 15, but not including it, that means that it's going to be everything greater than or equal to 16. So this would be X is greater than or equal to 16. Similarly, if I say that X is less than 18, that means it's everything below 18, not including it. So that means I go down to the next number. It is less than or equal to 17. So then setting this up, this means that we're actually going to find the probability of X equals 16 plus the probability that X equals 17, which, by the way, you don't have to write it this way. You could have actually just written it as probability of 16 plus probability of 17. I just wanted to do this so you can see that this means that probability that the random variable equals 16 plus probability that the random variable equals 17. And remember, our random variable for a binomial is going to be our possible outcomes. We could have 0 successes, we could have 1 success, we could have 2 success, up to n or all successes. Now, in order to solve this, though, what we need to do is we need to use our binomial probability. So if we have the probability of X, this is just going to be n choose X, probability of success to the X power, and then 1 minus the probability of success to the n minus X power. Or remember, 1 minus P is just equal to Q. So you could also just write this as n choose X, P to the X, Q to the n minus X. So solving for this, we first need to figure out what is the probability we get 16. So our n is 20, right? So n choose X. So this is going to be 20. Choose the probability, the number we want for our probability. Our probability of success, which we said was 0.19, to the 16th power, that's our X, and then our Q, which is 0.81, to the n minus X, so 20 minus 16, or 4th power, plus 20 choose 17, 0.19 to the 17th power, 0.81 to the 20 minus 17th, or 3rd power. And then from there, you could just solve this using the binomial probability like we've done previously in the course. Problem 22 says a veterinarian records the weights of cats treated at a clinic. The weights are normally distributed with a mean of 9 pounds and a standard deviation of 2 pounds. Find the weight X such that the probability of Z is greater than A equals 0.9948. So first thing I'm going to do, I'm going to write down what information we're given. So we have mu equals 9 pounds. And we have a standard deviation of 2 pounds. So if you were to encounter a problem like this, what is it asking us to find? Well, it says that we have the probability Z greater than A equals 0.9948. And we want to find the actual weight, or the X value, where this is true. So the first thing we're going to do is, first of all, we'll consider that this is an inverse probability problem. We're going to look at our standard normal. And if we have a standard normal with a Z that is, if it's greater than this value, where probability that z is greater than this value is going to be 0.9948. So where would our z have to be so that 99.48% of the data would have to be greater than that value? Well, in that case, this means we have to have a z way down here because we want 99% of our data to be above this value, right? So this means that z is negative. So in that case, what this means is that we actually are going to have to do some transformation because we can't look this probability up on our table because we don't have probabilities to the right on our table. So if this is 0.9948, this means that to the left of this, this has to be 1 minus 0.9948 or 0.0052. So we're going to go to our negative z table looking to the left and find 0.0052 to figure out what the z has to be. So going to our negative z table, we are going to go into the table and we're going to find the value that is closest to 0.0052. And I've already highlighted it here. And now what we're going to do with that is we're going to go over to the left side. We're going to get negative 2.5. We're going to go up to the top of the column and see 0.06. And this tells us that our z value has to be negative 2.56. Now from there, we can actually figure out what this x value would have to be, because what we're doing is we're now transforming to our normal distribution, which is centered at 9 pounds. And if our z value is somewhere way over here to the left, that means our x value has to be somewhere way over here to the left. So again, that 0.9948 is to the right of it. So we do this transformation by x equals mu plus z sigma. So then plugging this in, what do we get? Well, this means that we're going to have x is equal to 9 pounds plus negative 2.56, so minus 2.56, times 2 pounds. So I'm going to plug that in my calculator and we're going to see what we get. 9 minus 2.56 times 2, and we get 3.88 pounds. So what does this mean? This means that at the weight of 3.88 pounds, that based on the data this veterinarian has, where the average weight of these cats is 9 pounds with a standard deviation of 2 pounds, at the weight of 3.88 pounds, that means that 99.48% of the cats that they encounter should be heavier than this cat, should weigh more than this cat. Problem 23 says that we have NFL player Aaron Rodgers completes a pass 65.1% of the time. Find the probability that A, the first pass he completes in the game is his second pass, B, the first pass he completes in the game is his fourth pass, and C, he does not complete his first 2 passes in the game. So based on this, this is going to be a geometric probability distribution problem. And this is because we're looking at, based on the fact that he has 2 possible outcomes, he throws a pass, it either completes or it does not complete. So we have 2 possible outcomes. The probability does not change between passes according to this setup. So we have a P of, for 65.1% or 0.651, which means that based on this, he would have a probability of failing to complete a pass of 0.349. Now, if you remember, a geometric probability finds the probability of x, which is going to be that he gets his first completion on this turn, is going to be equal to p times 1 minus p to the x minus 1. And that is to say that if I got my first success, for example, in part B on the 4th pass, that means in order to do that, I would have to get a failure to complete on the first pass, fail to complete the second pass, fail to complete the third pass, and then finally get my completed pass on the 4th pass. So what we're doing is we're saying, what is the probability that he gets a failure, a failure, a failure, and then a success? And of course, we just use our multiplication rule, which is probability of failure times probability of failure times probability of failure, so n minus 1 of them, times probability of success. So A specifically asks that his first pass he completes in the game is his second pass. So we want to know, what is the probability he gets his first completion on the second pass? So this is going to be probability of success, 0.651, times the probability of failure, which is 0.349, to the 2 minus 1 power, which is just the first power. So really we're just finding 0.651 times 0.349. And plugging this into our calculator, we get, so 0.651 times 0.349. He has a probability of this occurring of 0.22719, so this is going to be 0.2272. Question B asks, the first pass he completes in the game is his fourth pass. So in this case, what this means is that he failed 3 passes and then finally got his fourth pass as his first success. So it's going to be the probability of success, so 0.651, times the probability of failure, 0.349, to the 4 minus 1 power, which is going to be 0.651 times 0.349 to the third power. Plugging this into our calculator, so we get 0.651 times 0.349 to the third power, and we get a probability of 0.02767, so I'm going to say 77. Part C is a little bit different because this one is more just the conceptual idea of not using the geometric probability, but also kind of thinking about what we're doing when we find those number of failures. Part C says he does not complete his first 2 passes. So if I threw a pass and I didn't complete it at a probability of 0.349, and I threw a second pass and I didn't complete it at a probability of 0.349, the probability that would occur is the probability of failing to complete a pass times the probability of failing to complete a pass, which is just going to be q squared. So it'd be 0.349 squared. So plugging this into my calculator, I get 0.349 squared, which is equal to 0.1218. And that is the end of our review for this exam. And I really do hope this has been helpful because it does take a lot of effort to do these, but I really do want to give you all the tools I can to help you succeed. That way you have a chance not only in class to follow along, ask questions, stuff like that, but now you'll have this video and the videos I've made for this so that you can kind of pause, go back, you can rewatch parts, and hopefully this will help with your understanding of the types of problems you might see or the things we might ask. Now, I do want to point out the fact that our exam is not going to be exactly one-to-one with this review, right? This review is going to be longer. Sometimes we'll put harder questions. Sometimes we'll change them up a little bit based on pacing and points and stuff like that. But I really do hope that this will help you succeed because 2 things. 1, the better you do in the exam, the easier it is for us to grade. But also the fact that I really do want you all to succeed when you're taking this course because these are all really important topics, especially the stuff we're doing right now, because most things in the world follow a normal distribution, right? Because chapter 5 covered such pivotal parts of statistics, like the central limit theorem, which explains why this normal distribution shows up in almost anything and everything. And by having a good understanding of this specific core set of concepts, you actually have the basis you need to understand a large chunk of statistics. So again, I really do hope this is helpful. I hope that you all can do well in the exam and be sure to study this, try your best. But remember that don't get too stressed about this. Don't put so much on this that you are causing yourself a ton of extra stress. And last is don't just try to remember what the equations are and how to use them. Try to actually understand it because that way if you hit a wall or a question that doesn't seem familiar, you can kind of hopefully logic yourself from all the things we've learned into figuring out how to solve it and what does it mean. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.